All right. Let's blaze through this. I want to point out this last link here. These are excellent height papers, or if you will, all of them are available here from Tom Meyer of UConn. He put them all together at this link. I mean, if you want to know the physics of these height systems, I mean, it's in there. Okay, so, you know, I mean, we're talking double, triple integrals and stuff like that, you know. But there's some basic things in the other, you know, there's 4 papers. Only one of them really gets really, really heavy about it. Excellent, excellent papers. Best I've ever seen. Cliff talked about HTMOD and the NGS study that they did in the late 90s and the value of it. It's been proven. And you can see some of the benefits here. They were very substantial. It far outweighed the fact that they weren't as accurate as geodetic leveling. You know, you can do geodetic leveling to millimeters. You can't do that with GNSS derived heights. And as far as I'm concerned, who cares? If I can get the national datum to 2 centimeters, that's great with me. The trouble is, there's not a lot of HTMOD stations. There's some in here in southern Louisiana, you can see. And that's good. That's very good. But where are those guys now? And I think we probably know the applications of height modernization. Sure, surveying and civil engineering is one of them. But man, the big buck is in precision agriculture. The farmers are running old mini GISs in rail transportation, highway transportation, FAA, the flights, and in shipping ports. I mean, if you can take one of these big liners, bringing a bunch of freight into a port, and you can reduce the keel clearance from this to this, you know, you're talking hundreds of thousands of dollars if you can just get the datum accurate enough. So HTMOD is a way to do that. There's a lot of applications. These poor people, the firm map wasn't updated. The elevations weren't updated. The impervious area wasn't updated. They got flooded. I mean, this was just completely decimated. And you're thinking, oh, those poor people in North Carolina. Well, guess who paid for that? We paid for that. Tax dollars did that, bailed that out. So HTMOD is pretty important. So we can just, you know, leveling is great, but it's very expensive, very time consuming. Can you imagine leveling to this point? I mean, it'd be your life's work, right? You'd start when you were 20 and you'd be finished when you're 75. You could just go up there and only do it to 2 centimeters. Oh, how sloppy. Who cares, right? It's nearly as good. Sometimes you need geodetic leveling. You can make ties with geodetic leveling. You can densify with geodetic leveling. But let's face it, you're not going to do extensive leveling because you can do it, the further apart you go, the better GPS becomes. As you can see here, the different classes. This is just the accuracy between points for leveling, if you will. Third order leveling, a couple millimeters times the square root of the difference in the 2 points. So 9 kilometers would be 6 millimeters between the points. You know, 25 kilometers would be a centimeter. You can see the further apart you go, the closer GNSS becomes to leveling, geodetic leveling. Well, you'll never reach that, of course, unless you go, I don't know, 200 kilometers or something. But the idea being that you don't have to do any of the requirements either. But it's not just standards of accuracy, it's specifications for leveling. You know, thermistors, leveling loops, tying to benchmarks, you know, precisions, things you have to do in the field. It's easier with GPS, of course. So that's the idea, obviously, right? These are things that you have to correct with digital leveling. You know, software will do a lot of it, but there's a lot of input as well. We're starting to get into the concept of different kinds of heights. I think we'll be okay. If you're leveling from point to point, the difference in leveling depends on the route you take, because you're traveling through different gravity surfaces, okay? Every time you set up optically, you're normal to gravity. So if you've got a gravitational attraction one way, you're going to be set up normally to that, and it's going to affect your leveling, of course, right? And then the other way, it's going to affect your leveling. So it depends on your route, what you're going to get between leveling. However, hopefully, using geopotential numbers, things like that, you're adjusting your leveling to get an orthometric height. Here's the idea. If you're leveling from point to point, you go up the hill to B, and you get a difference. You level down the hill to C, you say, you know what? This difference was equal to this difference. So A, the elevation to A is the same as C. Well, the leveling difference was the same, going up and down the hill, but because datum, the datum surface based on a gravity surface is not concentric due to the change in gravity from the surface to the datum. You go through different masses of gravity. So your line is a curved line. This surface is not parallel or concentric to any one of these other surfaces. That means that the orthometric height, which is the distance from this datum, NAVD 88, to this point, is different than this distance because they're not parallel. There's going to be a difference in those heights. That means that the orthometric height to A is different than the orthometric height to C. And the published value on the data sheet will say that. But if you leveled like this, as this guy did, you would say the elevation of A is the same as C. Okay, so just understand that the surfaces are not concentric, and leveling has to take that into account. Yeah, you go over a mountain or you go around the valley, you get a different answer. So of course you can do static, you can do real time, you can do autonomous point, precise point positioning. That's really coming into the fore now because they're using local augmentations of a global model for the corrections for orbits, clocks, ionosphere, that sort of thing. And they're using a local model to tweak it. And you actually can set up without any base station and get a point to, 2 to 5 centimeters. It might take you a little while, and it probably takes you half an hour to initialize, depending on where you are. But you can still get an answer. Of course, it's based on not on 93, but that's autonomous. Now, remember I said in 10 years, you're going to have a half a foot just walking around anyway with your pocket Ronco GPS receiver. And then what's another thing that's happening is the remote sensing is coming to be more accurate, or more precise, I should say. So unmanned aviation systems or aerial systems, you've probably seen it in the magazines where they have a little plane, you shoot it up in the air and it flies back and forth on the site and gets data around the site, like photogrammetry almost. So these are coming into play. I won't spend a lot of time on this. I think Tim Osborne addressed that. The thing I want to say here is they have tidal datum epochs, which are 19 years because that's how long it takes the moon to go through its nodes. And they average all of them out, come up with a tidal datum. How fast it changes, Louisiana is the same as Maryland. It's based on mean high water for property values. And we know how much change a little bit of difference in elevation makes. It'll go a lot further. And that's changing your property lines. So it's very important that we determine that as accurately as possible. This is what I was saying earlier. You have a tidal benchmark. Here's your 2 datum levels here. So if you leveled from here to here, you could tell whether the ground was subsiding or the water was uplifting or rising or both, right? Because you have this benchmark here. Well, suppose the benchmark's subsiding too. It doesn't tell you much, does it? But if you have a core station there, you know where the antenna is all the time. right? So you know if it's subsiding or not. Therefore, you always have a good handle on this. Is that water rising? Is the land subsiding? Or both. You know that with a chords. You don't know it with a mark in the ground. Tidal benchmark sheet. Etc. Okay. I think I can summarize this in time for lunch. We know about ellipsoid heights, right? We talked about that, and 83 ellipsoid heights from that global model of the world, that ellipsoid GRS 80. We talked about 29. We talked about orthometric heights. I'm going to show you the difference between an orthometric height and a dynamic height. NGS data sheet, here's the orthometric height. It's adjusted. Here is something called a dynamic height. Not the same. What is a dynamic height? Very simply, and there's slides to this I can go through. A dynamic height is a difference in geopotential. Geopotential, what is geopotential? Gravitational potential. How do you measure gravitational potential? Gravitational acceleration. How do you measure gravitational acceleration? In units of Galileos or gals. 1 centimeter per second squared is 1 gal. The difference in those two gravitational acceleration values gives a difference, a non-geometric quantity or value. Has nothing to do with the distance between those two surfaces. It's a difference in potential energy. But it means that everything on that one level, water will not flow. Everything on this other level, water will not flow. Not true with orthometric heights. So a dynamic height is given by, well, let's just get to the slide. I'm going to try to sum this up as fast as I can. Two geopotential surfaces. Let's call this the datum, W0. This is a point of interest at WP. The dynamic height is the difference in geopotential measured in geopotential numbers given by C, okay? And one unit being 10 meters per second squared. What is a meter squared per second squared? Well, it has no geometric concept. You can't picture a meter squared per second squared. It's a difference in energy. Okay? However, if you know that difference in energy, it tells you the difference in hydraulic head, it tells you a bunch of stuff that you know. And what you do, what they've done is just simply scale it by some kind of value for gravity, and you get what looks like a height in meters on the NGS data sheet. So you get something like this. That is an orthometric height. An orthometric height is a distance from the datum to your point. It's a distance. A dynamic height is not a distance. It's a difference in energy, potential energy. Anything that has the same dynamic height is on a level surface. Water will not flow. It can be the same as the orthometric height, or it could be different. It could have the same difference or not. What you're doing is simply scaling that meter squared per second squared by gravity on the ellipsoid at 45 degrees latitude. Just picked it out, you know. And that's what they use to scale all the dynamic values. Now here's the bottom line. You've got an equal potential surface. We're going to call this water an equal potential surface, right? Pretty much, unless you have wind or stuff blowing on it. This is another equal potential surface that we'll call the datum. Can you see that the orthometric height, or the distance from here to here, varies according to where you are, right? But the dynamic height is the same because it's the difference in energy between those two surfaces, which is constant. Okay? That's the difference between a dynamic height and an orthometric height. And yeah, it'd be nice to survey in dynamic heights because then we know where water is level, right? Exactly. But you can't measure it on the ground, you know. So it's not something that's readily available to us. You can, at the zero surface, Dynamic height and orthometric height are 0 together. The further you go up, the more they diverge. So when you get to Colorado or New Mexico, you know, you've got a low elevation here. The dynamic height's almost the same. You've got an elevation here of, you know, a little bit less than a mile, and you can see they're a meter different. That's just something to know, probably worthless information, but it's good to know that. The International Great Lakes Datum uses dynamic heights because they deal with shipping. They got to know where water level is. It would also be important for locks, say the Panama Canal. Okay. This is very simply, heights are geopotential numbers divided by some value of gravity. That's true for all these. Orthometric height, dynamic height, you know. An orthometric height uses the average gravity from the datum surface to your point. But there's no way to know that average gravity. So a helmet orthometric height uses a surface gravity. Now we're getting back to the importance of having good surface gravity. Okay? That's what we need to do in Louisiana at the RTN stations. So it uses surface gravity and uses this number here times the approximate height in kilometers, and you come up with a helmet orthometric height. So it uses surface gravity. That's the thing about orthometric heights. Okay? I'm not going to go into that any further. Do you need to worry about gravity? Well, if you're doing a small project, no. The geoid, this is in Maryland, so I don't know how these values relate here, but these are different geoids. Geoid 99, Geoid 03, Geoid 09, Geoid 12A. Can you see that they're kind of concentric, going from west to east? I mean, they sort of follow each other. The absolute value of them is different, right? They're not the same line. That's why you have to use the correct ellipsoid height to work with them, because each geoid is a different absolute value. If you use the right ellipsoid with them, then you come up with a similar orthometric height. And the point being here, probably not true here. Let's do this fast. If you've got a small project area, your difference in ellipsoid, well, it would be true to a certain extent here too. If you have a small project area, what are we going to say a small project is? Let's say a quarter of a mile, a couple thousand feet. Your difference in ellipsoid heights will equal your difference in orthometric heights, because the orthometric height does not vary that much in a small area. Okay, now I'm not saying that's true everywhere, but generally speaking, a small project area of a couple thousand feet, if you've got a benchmark and you're saying that was on the plans in 2006, it was on the plans in 2009, by God, they designed this bridge based on that mark. That is truth. Okay, but you're saying, I don't really know how to reestablish a orthometric on site that's going to match that. Well, maybe you don't have to. If that's your truth, you can use that and use differences in ellipsoid heights to be your differences in orthometric heights in a small area. Okay, because the difference is not that much. These are a mile apart. These are core stations a mile apart. The ones I have in red squares are the ones that really were high. But even if they're high, you've still only got 2.5 centimeters in a half a mile. So, you know, I mean, it's not that much. It's a tenth of a foot or something in a half a mile. Can you live with that? If you can, then you can use ellipsoid heights as differences. Okay. This is where I wanted to break, so we hit it. Kind of blasted through those last few slides.